going to work through 11 rotational practice problems covering angular acceleration, angular momentum, and energy. Let's begin. Problem 1 describes an electric fan slowing from 500 revolutions per minute down to 200 revolutions per minute in 4 seconds. We draw the fan and an arrow showing the rotation. Next, we convert both speeds to radians per second by multiplying by 2 pi over 60. Then we apply omega equals omega 0 plus alpha times t to solve for the angular acceleration. To find the total revolutions, we average the two speeds in revolutions per minute and multiply by 4 seconds over 60, giving about 23.3 revolutions. The angular acceleration is negative 7.85 radians per second squared. Problem 2 asks for the angular momentum of an electron moving in a circular orbit with a radius of 0.5 times 10 to the minus 10 meters and speed 2.2 times 10 to the 6 meters per second. We draw the tiny orbit, label the radius, and show the velocity arrow. Angular momentum is mass times speed times radius. Plugging in the numbers gives roughly 10 to the minus 34 kilogram meter squared per second. Problem 3 gives an angular velocity that equals 5 minus 0.8 times time squared. We sketch the decreasing curve and mention the variables. Differentiating gives angular acceleration equal to negative 1.6 times time. At 3 seconds, alpha is negative 4.8. The average acceleration from 0 to 3 seconds is negative 2.4, because the change in angular velocity from 5 to negative 2.2 over 3 seconds divides to minus 2.4. Problem 4 gives an angular acceleration of 2.25 radians per second squared for 4 seconds, while the wheel sweeps 60 radians. We show a wheel with a highlighted arc and label the angular distance. Using theta equals omega 0 times t plus 1/2 alpha t squared, we solve for the initial angular velocity and get 10.5 radians per second. Problem 5 has a flywheel that loses 500 joules of kinetic energy, while its angular velocity drops from 650 to 520 revolutions per minute. We draw a wheel labeled with the two speeds and an energy drop symbol. The change in kinetic energy gives I equals 2 times delta Ke divided by omega 1 squared minus omega 2 squared. Plugging in the convert speeds gives a moment of inertia close to 0.6 kilogram meter squared. Problem 6 asks about a wheel with moment of inertia 20 kilogram meter squared that gains 360 joules in 10 seconds. A spoke-based wheel with a torque arrow shows the energy input. Using half I omega squared equals energy gives omega equals 6 radians per second. With a constant torque, we find alpha equals omega over time equals 0.6 radians per second squared, and torque equals 12 newton meters. When we apply an opposing 4 newton meter torque, we solve omega final squared equals omega initial squared minus 2 alpha theta, which yields 90 radians before stopping, or about 14.3 revolutions. Problem 7 is about a ballet dancer starting at 1 revolution per second. When she pulls her arms in, she reduces her moment of inertia to 60% of the original. We draw a rotating dancer silhouette. Angular momentum is conserved. So I1 omega 1 equals I2 omega 2, which leads to F2 equals 1 divided by 0.6 equaling 1.67 revolutions per second. Problem 8 gives a propeller spinning at 1900 revolutions per minute. We show a propeller labeled with the speed. Converting to radians per second by multiplying by 2 pi over 60 gives approximately 190 radians per second. To sweep 35 degrees, we divide the radian angle by that angular velocity, yielding about 3.07 times 10 to the minus 3 seconds. Problem 9 accelerates a saw blade from rest to 140 radians per second in 6 seconds. We sketch a circular blade. The angular acceleration is omega over time, giving about 23.3 rad per second squared. The average omega is half of 140, so theta equals 70 times 6 equals 420 radians. Problem 10 describes a safety device that brings a blade to rest in 1 revolution, meaning omega final 0 and theta 1 revolution. Solving 0 equals omega initial squared plus twice alpha theta gives alpha negative omega initial squared over 2. When the initial speed is tripled, we plug into 0 equals 9 omega initial squared plus 2 alpha theta nu and find theta nu equals 9 revolutions. Problem 11 has a recording disk at 45 revolutions per minute, and a small mass is dropped onto it, making the new speed 36 revolutions per minute. We draw the disk and smaller mass at radius 0.04 meters. Conservation of angular momentum gives I disk omega 1 equals I disk plus Mr. squared, omega 2. So I disk times 45 equals I disk times 36 plus 19 millikilogram meter squared times 36. Solving yields, I disk equals 125 times the small mass times the radius squared, or about 1.28 times 10 to the minus 4 kilogram meter squared. We covered conversions, how to apply Newton's second law in rotation, energy methods, and conservation of angular momentum. Each practice problem reinforces a different key idea. Keep solving even more problems to develop deep intuition.